course, because I will put grade for your final grade. There will be part of your grade will be for the interaction during the class. So attendance is included and also interaction is included. So please let them know that it's not acceptable to leave the class. So welcome back to ME 760. So today we will be discussing a new chapter 11 from the book, which talks about the vector calculus. So the chapter will need a little bit of a review from chapter number 7, which is partial differentiation. So it is exactly the same, but instead of doing the partial differentiation, let's say, or integration of a normal scalar function, we will be differentiating or integrating a vector function. So let's start. So this is chapter 11, and it is vector calculus. And we will start with differentiating vectors. But before we differentiate vectors, as you know from the old, let's say, old lectures in calculus and algebra, we used to scalar functions. So a function f of r is, let's say, if r is in three-dimensional geometry, so this will be a function of x, y, and z, and it is not, where f is a scalar function and it's not a vector function. And can somebody give me a good example of a scalar function? Distance, yeah, speed. Or if we are talking about, let's say, T of R, which is the temperature in a field, for example, where R might be X, Y, and Z, or might be P of R, where P is the pressure. So those are two examples of a scalar functions. So this is a scalar function. Maybe we will have a vector function. Can you give me an example of a vector function? Velocity field. So we can define, for example, a function v. Now I put the arrow in top of v to indicate that it is a vector function, and I can decompose it to v1 of r in the direction of I in Cartesian coordinate, v2 of r in the direction of j, plus v3 of r in the direction of k. So what are v1, v2, v3? v1, v2, and v3 are the components of the vector v. And usually, as we stated before, we can write those as v1, v2, v3 in a component form like this. So if we want to do differentiation for a vector function like v, so we will have several situations. The first one, if, let's say, v of r is a single variable function, single variable function. So let's assume the variable now is t, time. So the definition of dv as a vector by dt, sometimes we write it as v prime vector. dv by dt is equal to v prime vector, and this is just will be the limit when the change in time will go to 0 for v prime at t plus delta t minus, sorry, v, not v prime, v at t plus delta t minus v at t divided by delta t. So this is just the normal definition of the differentiation for a scalar function. The only difference is v now is not a scalar function, v is a vector function. So this is exactly the same. So in component format, you can write it as v1 prime, v2 prime, and v3 prime. So dv by dt is dv1 by dt, which is v1 prime, plus dv2 by dt prime. So v2 prime will be dv by dv2 by dt, and v3 prime will be dv3 by dt. So this is in component format. And usually, if you have something like this, an arc, for example, and there is, let's assume that there is a particle here, and this is just, or this is a point in the field. This is v at time t, and v, let's say, at time t plus delta t, a fluid here, for example, at t plus delta t. So this is just delta v here, and this is the origin. So this is the velocity tangent, and this is the velocity here. So what are the properties of differentiating a vector field? The first property is if you have to differentiate a constant multiplied by a vector function. So what's the result of this? Alpha v prime vector, because alpha is a constant. So if you have to differentiate two functions, u plus v, what do you think? So this would be the differentiation of the first function plus the differentiation of the second function. The third property would be if you have dot product for two functions. So we knew from the scalar multiplication or a scalar functions, let's say, f of x multiplied by y of x. When we try to differentiate something like two functions multiplied by each other, we use what rule? The partitioning tool. So it will be the first multiplied by the differentiation of the second plus the second multiplied by the differentiation of the first. So this would be u prime multiplied by dotted with b, but because we are using vector, I have to put the dot product plus u dotted with v prime. So now, instead of dot product, we knew from vectors that we do not only have a dot product, we have what? Cross product as well, and we have three products. So for the cross product, u cross v, and we want to differentiate this. This will give you u vector crossed with v prime plus u prime vector crossed with v vector. Again, we use the same partitioning tool. So here we have u v omega, so I can do it exactly the same. I did not put any here, anything, whether it is dot or crossed. This means that you can do any combination. U dot V dot omega or whatever. Of course you cannot have it. U dot V dot omega, why? Because U dot V is a scalar and you cannot dot scalar with a vector. So U dot cross or U cross dot or something like this. So I will leave it like this. So what you will do is you will say the first multiplied by the differentiation of the second plus the second multiplied by the differentiation of the first. But the second is composed of two vectors, so I have to do again the same rule again. So this will give me the following. So the first u prime, so this is the derivative of the first one multiplied by the second one, v omega, plus, now you differentiate the first and you keep the second one, then you keep the first one, which is u, and then you multiply it by the differentiation of vu. So the differentiation of vu is again v prime multiplied by omega plus v multiplied by omega prime. So this is just the differentiation by part. So we define the situation when we have a single variable function. What if we have a function f or a function v of several variables, t1, t2, t3 up to tn. So those are the n independent variables. So n independent variables. So in this case, we will replace the total derivative by what? By a partial derivative. So this will give me dv by dt. But in this case, I will pick up one of those i's. Let's say I want the derivative of v with respect to t3. So this will give me, because the velocity field has three components, v1, v2, v3 in I, j, k. So this will give me dv1 by ti in the I direction plus dv2 by ti in the j direction plus dv3 by ti in the k direction. So just you differentiate the relevant components of the vector v1, v2, v3 with respect to ti. So what if I have the independent variable t is also a function of another variables, s1, s2, s3, and so on? So what do you think? What should I use? The chain rule. So special case of this is when you have v, or when you have ti is equal to ti of s1, s2, s3, and sn. So the function t is another function of s1, s2, s3. So how we will obtain the, let's say, dv as a vector by dSi. Let's assume I want to calculate the partial derivative of my vector with respect to S3. So this is just the summation over j equal to 1 to n, and this will be dv as a vector with respect to tj multiplied by dtj by dSi. So what we are saying here is, if I want to calculate the partial derivative of v with respect to the independent variable Si, so this will be the rate of change of v with respect to tj, which is how many t's here? N. So this will be dv by dt1 multiplied by the partial differentiation of t1 with respect to, let's assume that Si is S3. So this will be, let's assume Si is S3, and we have n equal to 4. So let's make it here. dv by ds3 is just equal to what? dv by t1 multiplied by the t1 by ds what? 3 plus dv by t what? 2 multiplied by the d22 by s3 plus dv by the t3 dt3 by s3 plus dv by what? t4 multiplied by dt4 by ds3. So this is equivalent to this. Okay, guys? So just using the chain rule, if you want to calculate dv, of course, all of this will be vectors. We can get a special case of this now. If we want to calculate the derivative, but now v, the vector v, is function of s and the t's, t1, t2, up to tn. So a special case when you have the function, the vector function v, as we stated here, was a function of what? t1, t2, t3, and tn. Now the function v is just v of t1, t2, t3 up to tn, and also s. It's not s1, s2, s3. Let's say just s. And each one of those, t1 is a function of s, t1 is a function of s, and t2 is a function of s, and tn is a function of s. So now, if I want to calculate the total derivative now, this is why I call it d capital by dt. So how to calculate the total derivative now? By ds, sorry. How to calculate this? So usually you calculate this by calculating something called the differential, and we'll take the definition of differential in a second. So you will say dv, the total change in v, is equal to what? d vector v by the ds multiplied by what? ds plus, then you will say dv by d what? t1 multiplied by what? dt 1 by what? By ds multiplied by what? By ds plus dv by dt2 multiplied by dt2 by ds multiplied by ds up to dv by dtn by ds multiplied by ds. And if you want to get this with respect to ds, you have to divide by what? Ds everywhere. So I divide by ds here, I divide by ds here, I divide by ds here and ds here. What happened for ds over ds? Cancel out. Yes? So this would be what? dv vector by ds plus, this is just 1 everywhere. I can put this in a summation form as j equal to 1 to n dv by dtj multiplied by dtj by ds. Does it make sense to you guys? Do you have any question here? So this is dv by ds. So again, this will lead me to the definition of differential, total differential. So this is differential of a vector. So if the vector function is a function of many independent variables, to get the differential, all what you will do is just, you will say the total differential of v is nothing more than dv by dt1 multiplied by the change in t1 plus dv by dt2 multiplied by the change dt2 plus up to dv by dtn multiplied by delta tn. So this is just, and again we can write it in the same format here, and we write it as what? dv summation by dt I dti and I equal 1 to n. So we can define what we call mean value theorem for vector field now. And the mean value theorem shows that if you have the origin here and you have a vector r0 and there's another vector here which is r0 plus certain delta, and you have some point b star here. So if we have a function of a point here, let's say evaluate the function here. So this is a vector field, and we have a function of x, y, and z in this vector field here. So f of x0 plus alpha and y0 plus beta and z0 plus gamma, where alpha, beta, gamma are just the components of the vector delta. So vector delta is equal to alpha I plus beta j plus gamma k. So this is the vector delta here. So if we want to evaluate the function here, let's say at x naught plus alpha y naught plus beta z naught plus gamma, which is the function at r naught plus delta. So the function at r naught plus delta. So it will be f x naught plus alpha y naught plus beta and z naught plus gamma is just equal to a function at x naught, y naught, z naught plus alpha multiplied by the differentiation of this function with respect to x evaluated at some point b, which is on the line or vector that represent delta, because this is just r naught plus delta and this is r naught, so this vector is just delta. So some point here, so this would be beta multiplied by df by dy evaluated at this point p plus gamma df by dz evaluated at this point p. So now we just show how to differentiate a vector function with single variable, how to differentiate a vector function with multiples of independent variables, so t1 up to tn, and we show the case for when each one of those independent variables is also a function of another, let's say, independent variable, which is s, and we use the chain rule to calculate the total derivative and also the differential. Okay, now let's look at integrating vectors, the vector function, integration, excuse me, integration of vectors. So let's assume that we have a vector function A is a function of the independent variable u, and this function can be represented as the total derivative of another function A, capital A, of the same independent variable. So in principle, you can represent a vector function of a single variable as a total derivative of another function of the same independent variable. You can do it like this. So then we will note that the integration of this vector function A of u over delta u will be just the vector function A of u plus another vector constant here, like b. Can somebody give me an example of this?
Integrating the velocity to find a position?
Yes, to find the position, or integrating the acceleration to find the velocity. So in this case, this will be what? The acceleration field, and this will be what? The velocity field. So you will differentiate the velocity field to get the acceleration field, or you integrate the acceleration field and you get the velocity field. And then you will have your constant will be what? If you are talking about initial value problem, will be something like the initial vector velocity. So this is why we put, instead of a constant, we put what? A vector. Because let's say you'll assume, okay, I started at V in the three component, V1 naught, V2 naught, and V3 naught. So this would be the initial value for the velocity field. Okay, guys? So this is just show you an example here. And of course, we will give a couple of examples. Other one is if you integrate same function, let's say acceleration, from u1 up to certain value of the independent variable u2, this will just give you a of u2 minus a of u1, because this is definite integral and this is indefinite integral. So with the indefinite integral you have to put what? A constant. And with the definite integral, it is the integration at the upper limit minus the integration of the lower limit, and this is what you see here. So what's the application of the vector integration?
Excuse me.
Huh?
Sorry, I missed that part. What's that P star there? There fx minus.
This one?
Yes.
This is the point here.
A point on that vector.
Yeah, and the vector delta, because this is R naught plus delta, and this is the vector
It
delta.
can be chosen arbitrarily.
It's midway between both.
Midway.
Yeah. Or, yeah, midway. Okay? So, do you have questions so far? Any other question? Okay, so the application, let's look at application for vector integration. One of this application is to find if you have a particle, a smaller particle, revolving around a larger mass particle. So this is M capital, and there is a M smaller here, and this particle is just rotating around M. So this is M small, and this is R. This vector is vector R, and the direction of this vector R is just R small. So if mass M is very much smaller than the capital mass M, like in gravitational, for example, field. So let's assume that this is the Earth and the Moon, and you can neglect the mass of the Moon with respect to the Earth. Or there is another planet in our, let's say, Milky Way, or in the solar system, there is another planet, for example, and I assume that there is a very small moon that rotates around this planet, that you can neglect M. So in this case, we can write the equation of motion, force equal to mass multiplied by the acceleration, as m d2r by dt square equal to negative, the gravitational force is just g multiplied by smaller mass, capital mass, over r square, and this would be in the direction of r. So m cancels out because it is in both direction. Then we can write this as d2 square r vector by dt square equal to gm over r square in the direction of r. If I cross product with this equation, a vector r cross product with this equation, so I can write this equation as what? R cross d2 r by dt square equal to negative gm divided by r square, and this will be r cross r small cross r. Yes? But what's this? R hat cross r. The value of r hat is what? is 1, and it is in the same direction of what? So what's this? 0, because this is cross product. And the cross product of two vector, collinear vector is what? 0, because this is collinear. Okay. But if I want to do the time derivative, to see what is the time derivative of r crossed with dr, so d by dt of r crossed with dr by dt. This comes from what property that we used to write 5 minutes ago or 10 minutes ago at the early beginning? We wrote this property. Vector A crossed with vector B primed is equal to what? The first multiplied by the differentiation of the second plus the second multiplied by the differentiation of the first. And multiplied by here means cross or dot. And we have here cross. So this will be what? This will give me what? R crossed with d2r by dt squared plus dr by dt cross what? dr by dt. What's this?
0.
Why?
Same vector.
Same vector. And what's this?
0.
From over there, look at over there. R crossed with d2r by dt squared is equal to 0. Yes? So what we say is this differentiation of some vector is equal to 0. What does it mean? When you differentiate something and it gives you 0, what does it mean? It's a constant. So this means that this term is just constant. So r cross dr by dt is just a constant. So what does it mean? And I call it C. It means that r crossed with dr by dt, and this is motion. So this is a constant of what? Constant of this motion. And what's dr by dt is what? Is velocity. So r crossed with v. Do you remember what's r cross v? Angular velocity. And if you are rotating, okay, the angular velocity should be a constant of motion here in a circle like this. Yes, guys? So let's look at the interpretation for our, let's say, solar system, where you have, this is the orbit, and this is the sun here, and the earth is at certain location here, at certain moment of time, at t1, and at t2 comes here. Then if you want to calculate this area, this is what? Nearly a triangle. Yes? So this is vector r at t, and this is the same vector at t plus delta t. So what is the area here? This area A is equal to half multiplied by r crossed with dr by dt, because this is just dr. Yes, guys? So it's half half r crossed with dr by dt, if this is just dr, sorry, crossed with dr. So the time rate of change of the area will be just what? Half r dr by dt. So this is the constant of motion. Yes? So this is the constant of motion here. Okay? And we showed that the time rate of change of area is equal to what? Constant. What law? Do you remember? I heard some initial Kepler name or something like this. So this is one of the Kepler's law that state that the planet around the Earth will sweep constant area per unit time, or same area per unit time. Yes? So the area, the sweeping area is the same. So if you are from here to here, so this area, let's say, if you divide this area by the time it takes the planet to move from this position at T1 to this position at T2, it is the same area here. Okay, guys? So this is one of the applications. Okay? So now, let's look at vectors in 3 dimension and how they are represented and so on. The material in this chapter is trivial compared to the vector spaces and eigenvalues and eigenvectors, and so hopefully you will enjoy this material. Although we will spend only 2 more lectures and we will be done with this chapter. Then we will move on to chapter number 12, which is the surface integrals and so on. So curves in 3 dimensions. So we can represent these vector functions in several representations. One, we call it parametric representation. Parametric representation. What do we mean by parametric representation? So if you take calc, let's say advanced calculus or calc 2 or whatever, I don't know what's the course number here for calc 2 or calc 3 or whatever, you will have parametric representation. So if you have a function, let's say, of x and y, then each one of these x and y is a function of time. So this is called parametric representation, for example. So let's assume that x, let's say, is this cosine omega t, a cosine omega t, and y is just sine a sine omega t. So this is called parametric representation of the function itself. So if you want to get, let's say, a circular motion, so you can define, excuse me, you can define a circle, excuse me, you can define a circle as what? A circle has a radius r, and you can define r as what? X squared plus what? Plus y squared. So also you can define the circle as what? As r equal to a, and then x will be what? X will be what? A cosine omega t, if there is a particle rotating here, and let's assume there is a particle here rotating, and there is an omega angular velocity here, and y will be what? A sine omega t. This is the sine part. So this is y. So you can represent it as this, or you can represent it as this in parametric representation. So a vector r of u is just x of u and y of u and z of u. So it's exactly the same like here. We have two dimension. The vector r will be a function of x and y, and the vector r, let's say in two dimension, I can write it as r of t will be just x of t and y of t. So it is exactly the same. I represent the vector r as a function of the independent variable t, which is in this case is the parameter, because each one of the components of r in x and y is a function of the same parameter. Okay, so this is the parametric representation of the vector. And this means that this is xi plus yj plus zk. We can have also explicit representation for the vector. Instead of just parametric like this, we can have explicit representation, and we'll have something like y equal to a certain function f of x, and z is equal to g of x. And in this case, if we are, for example, talking about circle, in the x, y, and z equal to 0, and this is x, and this is y, for example, we'll be able to show that y is just r squared minus x squared. So we do not have any parameter involved here. It's like this. This is the explicit form. This is the parametric form. Okay, guys? So if, let's say, u is equal to x, for example, the vector r can be represented as u f of u and j of u. So x, just if we set x equal to u, so it will be x equal to u and y equal to f of u and z equal to j of u. We can also look at intersection of two surfaces in a space. And this is from chapter number 9. So intersection of surfaces. So if we define, let's say, two surfaces, one is f of x, y, and z is equal to 0, and another surface g of x, y, and z is also equal to 0. So let's define the first surface to be just f of x, y, and z to be just x squared minus plus y squared, x squared plus y squared minus r r square. So this is just a cylinder around the axis. Around the axis with the radius r. So if we plot this cylinder, we have something like this. And let's say so this is the z-axis, and this is x and y here. And if you define g of x, y, and z is equal to 0, so is equal to z. So what's the equation of z equal to 0? Z equal to 0. If I give you an equation, I say z equal to 0. This is equation of what? Huh? It's a plane that cuts the z-axis at what? At 0. And where it lies? XY plane. So this is the XY plane. Yes? So z equal to 0, this is XY plane. So the intersection of z equal to 0 with this cylinder will give me what? So if we have so the intersection will give me a circle like this. Then we can define, and this will be the last part of this lecture, how to calculate a tangent in three-dimensional space for a vector field. So how to calculate the tangent. So if you have an arc like this, and then you have r at u, and this is r, vector r at u plus delta u. So this would be what? Delta r, sorry. Delta r. So let's say that this is a line L that passes through the delta r, and also delta r here is just, we'll call it a vector S. So the tangent here at this point does not cross this S here. Does not cross it, just tangent to it. And this point, let's call it P. And the direction of the tangent, let's call it R prime. R prime vector. So just this point is B, this point is Q. L is the direction. L has direction. The direction of L is just 1 over delta R, or let's say we'll divide by delta U here, and we'll put as R of U plus delta U minus R of U. So this is just equal to 1 over delta U multiplied by S, the direction of S, because R at U plus delta U is this point, minus R of delta u is this point, so this is delta, this is s, the direction of s. So, yes? So this vector is what? Is the s vector. If you divide it by delta r here, we call it delta r here, r at u and r plus delta r. If you divide it by delta r, this is actual delta r. If you divide it by delta r, what this will give you? Which is the, delta r is the amplitude of s. Amplitude of this amplitude. So this will give you what? A unit vector, which will be s hat or something like this. So in this case, if you take the limit for this, if you take the limit for this, the limit for r of u plus delta u minus r of u divided by delta u, this will give you what? When delta u equal to what? 0, this will give you the r r prime vector. So I will stop here because I am run out of time and continue next time. I will reiterate in this next time. Did you have any question so far? Okay.